One of the non-neural network comparative models we used was XGBoost, which, as you may know, is an example of boosted trees. There were several motivations for us using XGBoost. First of all, it used to be a very popular image classification algorithm before convolution neural nets became the go-to algorithm. Also, the supervised learning paper from Paper Discussion 2 showed that boosted trees were very successful in many classification tasks. Furthermore, XGBoost tends to be faster compared to many other boosting algorithms due to it being very easily parallelizable. In creating XGBoost models, I attempted to fit the models that predict car model types. Because the image dimensions needed to be scaled down, there were some data preprocessing that needed to be done. To reduce the image dimension from 3D to 2D images, I used two types of 2D images. One was grayscale images, which basically took out the RGB values from all images. The second one that I was using was the edge detection method, which is a feature extraction method that Sean mentioned previously. I also modified the image sizes so that all images were 100 by 50 pixels, so that all pictures will have a 2:1 aspect ratio. This will introduce some image distortions, which will most likely impact the performance metrics. In the future, I intend to compare more feature extraction methods. Due to time constraints, I couldn't put too much thought into the hyperparameters used in this initial run of XGBoost. I used pre-existing XGBoost classification code, with the only modification being reducing the max depth parameter to 3 in order to speed up the process. With these hyperparameters, I obtained these testing results. The grayscale model generated a result equivalent to random guessing. However, edge-detected data shows sign of significant improvements, with accuracy and F1 scores 5 times better than grayscaled images. The confusion matrices also reflect these results. As you can see in the confusion matrix of the grayscale image model, the plot is mostly white noise-like, which means that it really isn't predicting anything. Compared to that, the edge-detected model appears to have a bit more structure, with a very faint diagonal line that can be seen. This line is most likely the correctly predicted models. There were several takeaways after running these initial XGBoost models. First of all, hyperparameter tuning is going to be key in obtaining a good model, so I'll be doing a very extensive grid search. Also, feature extraction seems to be improving the model performance, so I'll be looking into different types of feature extraction methods. Also, to reduce runtime, I'll be trying to create multi-node structures.